It turns out that if we organize the Gaussian elimination computation in a particular way, then we can actually write down a factorization of the matrix in terms of two terms which are easier to deal with than the original matrix. So that's what we're going to show you here. We start here with the same matrix as in the previous video that we did Gaussian elimination on. So it's a 4x4 system. We're not even going to pay any attention to the B vector for now. It'll just be the A matrix that we're going to deal with. So when we did the row operations that represented Gaussian elimination, remember we produced these three unit lower triangular matrices. So the first one, L, is what we used to put zeros into the first column of A. And then we multiply by M to put zeros into the second column. And then we multiply by N to put a zero in the third column. And what was left was upper triangular. Right? That was the whole point of doing the Gaussian elimination, was to end up with an upper triangular system. So we have to first apply L on the left, right? We're doing row operations, so we multiply on the left, then M, then N. And the result must be U. Okay. Now it turns out that we're getting a little bit of luck here. So if we write out, first we can use the associative law of matrix multiplication, right, to group those matrices this way. And then we could write that A is the product of two matrices. So we multiply by the inverse of that product on the left times U. Right, so if we take the line above, we multiply by NNL inverse on the left side of both sides of that equation, this is what we get. And that should mean that A is equal to, and this goes back to a property of matrix inverses. The inverse of a product is the product of the inverses in the opposite order. Okay, which you can check just by multiplying them together and getting the identity matrix. Alright, so now our first bit of good news is that if we look at these individual matrices, L inverse, M inverse, and N inverse, so here's L again, it turns out that the inverse of L is incredibly simple. Just take the entries below the diagonal and turn them into negatives. So 2 became negative 2, negative a half became 1/2, 1 became negative 1, and that's it. Same is true of M. Take the inverse of M. You see all we had to do was take the negatives of these entries below the diagonal. And the same is true for N as well. Now, this really isn't an accident. There's a good reason for it. So if we look at a matrix like, let's take M, for example. So M, almost an identity matrix, right? Plus, we have a matrix which is 0 everywhere but in one spot. Like that. Well, it turns out that we can write this matrix as an outer product of two vectors. So we can do that by using -0, 0, -3, 0 times 0, 1, 0, 0. So if you compare the outer product of those two, it's pretty clear, right? 0 times that row, 0 times that row, -3 times that row gives us the -3, and then 0 times that row again on the bottom. And now we can just write that as I plus some vector, I'll call it V. And then this is a column of the identity matrix. It's the second column of the 4x4 identity transposed. Okay? So it's pretty easy to check that if you take I minus v, v2 transpose, times I plus v, v2 transpose, well, we get 4 terms just by multiplying this out. And remember that we can't just change the order. Keep things in order. Okay, so that's just multiplying out those 4 terms. And then we use the associative law here. Okay, E2 transpose times V, that's an inner product of the 2 vectors up here. Well, the inner product of E2 with V is just 0 times 0 plus 1 times 0 plus 0 times negative 3 plus 0 times 0. In other words, it's just completely 0. And of course, these 2 terms cancel each other out, and so the whole thing is just equal to the identity. In other words, right, this guy, which is M, no space here, so M, remember, is I plus VE2 transpose, and so therefore M inverse must be I minus VE2 transpose. And that explains why, when we take the inverse of M, all we have to do is turn that entry in V from a negative 3 into a 3. All right. So that's true of all of the particular matrices that we get when we're doing Gaussian elimination. I should emphasize that this property is not true for every triangular matrix. It's not even true for every unit lower triangular matrix. These matrices are special. They have non-zeros, or I should say, they differ from the identity in only one column. And that's key to making this property work. Okay, so to rewind a little bit, remember we have, from Gaussian elimination, that A is the product of these 3 matrices times an upper triangular matrix. And now we know that these 3 inverse matrices are really easy to write down. The numbers that we're talking about in the lower triangle are the row multipliers. So all we have to do is just take the negatives over our row multipliers, and we can easily produce those 3 matrices. The second surprise happens when we multiply those 3 matrices together. So remember, the inverse of L, the inverse of M, and the inverse of N are each very simple with they're differing from the identity in just 1 column each. When we multiply them together, all we do is put those triangular elements together. In other words, the elements that appear below the diagonal here are just exactly the ones that appeared in L, or L inverse, M inverse, and N inverse. Okay? They're exactly the same as these numbers. That's really easy to explain with the linear algebra 2. I won't go through it, but it is in the book. So now what that tells us is that A is equal to this matrix, which I'm now going to rechristen as L, times U. So L is equal to our old N inverse, M inverse, L inverse. L is a unit lower triangular matrix. Its entries are the row multipliers. Of Gaussian elimination. U is upper triangle. Its entries are the result of doing all the eliminations. So here we can write our first MATLAB function for the course. Okay, a function is very much like a script in that it's a sequence of commands that's processed by MATLAB, but it always starts with this word function in the first line. Then you have one or more, actually 0 or more, output arguments. And over here you designate 0 or more input arguments. Okay, so what this says is that when this function LUFact is called, A will be provided by whoever is calling it. So what the matrix that we call A in this function was provided to us from outside. Okay, once we're done, A disappears. It's only a local definition of A. It's called variable scoping. Meanwhile, we will construct two matrices, L and U, which will then be returned to whoever called us to do with whatever they please. It's a nice idea when you write functions to give a quick description of what it does and what the inputs and outputs mean. Always good for reminding yourself later. Okay, and here's the algorithm. So again, with the matrix A, we're going to assume that it was square when it was passed to us. A better program would check that for us, but to keep things short, we don't do those kinds of checks in this course for the most part. So we're just going to look at the length of A, which is just the longest size, the largest dimension, which should be the same in both dimensions. So N is the number of rows and the number of columns of A. We're going to start off L, which will be our unit lower triangular matrix, as an identity, and we'll just fill in the lower triangle from here on out. So now we do the elimination. So we loop over J, that's the column where we're introducing zeros. Okay, in each column, in column J, we have to put zeros below the diagonal. So those are rows J plus 1 to N. We come up with the row multiplier that we're going to use. So this is what's going to multiply row I in order to do the elimination. I'm sorry, it's what's going to multiply row J in order to do the elimination in row I. And we store that in the matrix L. And then we do the row operation in the next line. Which makes the proper element equal to 0. So it makes the ij element equal to 0. At the very end of the function, after we've done all the loop through all the rows and columns, we then just do this last command here, which forces all of the elements in the lower triangle of A to be 0. So if some of them were not quite 0 due to round-off errors, this will just make them exactly 0. Alright, so this function will then take a square matrix A and return L and U triangular matrices so that L times U is equal to A. Now, to go back to the linear system then, if we do have a linear system AX equals B, how does this help us solve it? Well, A is equal to LU, so we can substitute for A here. And then we can use the associative property, right, to say that this is actually two equivalent statements. L times some vector Z is equal to B, where we define Z as U times X. So it's pretty clear to see the mathematical equivalence there. So algorithmically, we start with B, So we're given A and B. Find L and U, factorize A. And you solve LZ equals B for Z. So you know L and Z, or you know L and B, you can find Z. That's a forward substitution. And then you solve Ux equals Z for X, and that's a backward substitution.